Our next speaker is Professor Dong Han from the School of Mechanical and Power Engineering in Shanghai Jiaotong University. Professor Han received his PhD degree from Shanghai Jiaotong University in 2012 and was then a postdoc at Shanghai Jiaotong and then Princeton University. Then he served as an associate professor in the School of Mechanical and Power Engineering at Shanghai Jiaotong since 2016. Thank you. Please go ahead.
Good morning, ladies and gentlemen. Okay, and my name is Dong Han, and I'm from Shanghai Jiaotong University. It's my pleasure to give a report at the COST Research Conference, Hydrogen-Based Mobility and Power. And the topic today is explosion limit and energy conversion in flames of hydrogen and ammonia mixtures. And I'm sorry that I couldn't be in person in this conference. And thank you very much for the invitation. So maybe everyone knows that many countries in the world has signed the Paris Agreement to reduce the carbon emissions and the temperature increase. So we have to face and satisfy the stricter limits on carbon emissions. And this is why we need to seek some alternative fuels to be used in the power and mobility sections. So that's why we are trying to seek some low carbon fuels. For example, the dimethyl ether and also butanol. And this part of fuels, we have done something on their combustion fundamentals and applications. And I have reported in the previous conferences. And another type of fuels is the carbon-free fuels, or we call it zero carbon fuels. So these fuels include the ammonia and hydrogen. So these fuels, we also did something in the recent years. And in this report, I will discuss something on the combustion characteristics of ammonia and hydrogen mixtures. So here we comes to the blend, to the background of the ammonia and hydrogen blend combustions. So in this report, I will discuss two parts of researches. The first one is the explosion limits of the change binary mixtures of ammonia and hydrogen. And the second part is on the Exergy destruction sources in the premixed flames. So first we come to the explosion limits of hydrogen and ammonia mixtures. So for explosion limits, it's usually defined as a pressure temperature boundary separating the explosive and non-explosive regimes. And from the left side figure, we can see it's a typical C-shaped curve for the hydrogen fuels. And the explosion limit is an important characteristic of a homogeneous fuel oxidant system. To identify the explosion limit, it could help us explore the critical conditions of chemical runaway and identify the controlling reactions in fuel explosion and also form the foundational block of fuel oxidation. So that's why we come to discuss the explosion limit of ammonia and hydrogen mixtures, because these zero carbon fuels, when they are used in application, we have to have some concern on their safety, and the explosion limit is quite related to this, and the explosion limit is also a combustion feature of the fuels. And then we did some sensitivity analysis and eigenvalue analysis for the explosion limit of the mixture fuel. We try to build a linear mechanism for the fuel blends to capture the explosion limit characteristics. And finally, we try to modify this model or mechanism, is a reduced mechanism, and try to capture the explosion limit characteristics at even higher pressure. Okay, so this is the contents of the first section. And for the calculation specification, we have 4 things to say. The first one is the calculation model. It's an adiabatic homogeneous zero-dimensional spherical reactor with a radius of 3.7 centimeter. And the mixture is a stoichiometric ammonia, hydrogen, and oxygen mixtures. The chemical kinetic model we used is a May model developed by SGTU and published in 2019. It has 38 species and 265 reactions. And third, the explosion criterion is defined as a 50K increment during the first 0.5 seconds in the reactor. And the fourth part, we also did mechanism reduction because we tried to do the eigenvalue analysis, which cannot be done using a detailed mechanism. So we use DRG and the SA method to generate a reduced mechanism first. Okay, so first we come to see the explosion limit of ammonia and hydrogen blends with different composition. And we use detailed and reduced mechanism for this comparison. So first we come from the maze mechanism, is we call this a detailed mechanism. And then we use DRG and SA to generate 2 reduced mechanism. Mechanism 1 has 26 species and 188 reactions. And mechanism 2 has 26 species and 82 reactions. And the simulation results of all the detail and the reduced mechanism, we can see they generate a quite consistent explosion limit curve for different fuels. And from this figure, we can see if we use the pure ammonia, the explosion limit is a monotonic curve versus temperature and pressure. But if we get hydrogen added into the fuel, we can see the explosion limit curve change from monotonic to a Z-shaped non-monotonic curve. And also, if we get the hydrogen percentage even higher, we could see the lower explosion temperature at a given pressure. So this is what we see here. Get some hydrogen into ammonia, and the explosion limit will change to the quite similar with the hydrogen explosion limit curve. Is a 3-sectional explosion limit. Further, we did a sensitivity analysis, and this sensitivity analysis first done at a low pressure condition. And from this figure, we can see for pure ammonia, the reactions involving hydro-nitrogen are quite dominant. So we can see it from this part. And also for the mixtures of ammonia and hydrogen, we can see the NH2 related reactions are quite dominant. So we can see something change because the fuel combustion chemistries change. And for elevated pressure conditions, for pure ammonia, the reactions involving NH2, nitrous oxide, and H2NO play an important role. And the ammonia hydrogen mixtures, we can see is right here. The H2O2 system reactions become more dominant when we get hydrogen into the blends. And the reactions involving H2O2 and H2 are quite enhanced. Okay, so now we have come to the combustion chemistry for the ammonia and hydrogen explosion process. And further, we try to do the eigenvalue analysis and generate a quite small mechanism to predict the explosion limit. And first, because for the explosion limit calculation is an homogeneous system. So first, we try to generate a linear mechanism. We call it the linear mech. So we do it based on the mechanism 2. It has 26 species and 82 reactions. We extract the molecular reactions and the radical molecular reactions out of the MEC2 mechanism and generate a mechanism of 18 reactions. So we call it linear mechanism because all of them are molecular or radical molecular reactions. So now we have this mechanism, and we try to establish a matrix for further analysis and calculation. And for this matrix established, we consider the wall destruction reactions. So here is the reaction described here. So R becomes absorbed products by wall destruction, and here Ki is the reaction rate coefficient. So it's a function of E, which is a leaking coefficient. The V is a thermal diffusive velocity, and S, V, which are the surface and volume of the reactor. And also here we define competition coefficient between ammonia and hydrogen chemistry. So here we can see we have 3 competition coefficients, which are alpha, beta, and gamma. So alpha is for the O radical. It describes the O radical consuming in the R2 reaction, which is the hydrogen chemistry. And R13 reaction is related to the ammonia combustion chemistry. So alpha is a parameter describing the percentage of O radical consuming in the hydrogen chemistry, and so forth and so on. Beta is for the OH radical, and gamma is for the HO2 radical. And they describe the radical consumption percentage in the hydrogen chemistry channel versus the total consumption chemistry channel. And now we try to build this matrix. And for this matrix, we can see is dx divided by dt equal to L times x plus n. And x is a vector of species concentration, including H, HO2, H2O2, and NH2. And L is the matrix describing, so L times X describing the production rate of these radicals by the chain propagation reactions. So this is the Lx. And also we have a matrix N. So N here describe the radical production rate based on the chain initiation reactions. And from the matrix L, we can see that the alpha and the beta, these competition coefficients only occur in the first row and the last row. So that means these two reactions are quite close to the generation and the consumption of H radical and the NH2 radical. But for the gamma coefficient, it occurs in the second and third row. So that means it's quite related to the HO2 and H2O2 chemistry. Okay, and now we have this matrix. So then we try to make the determinant of matrix L equal to 0. And then we make an assumption the gas in the reactor is ideal gas. So in this way, we can make the collision molecule refers to the function of P and T. So now we can plot the explosion limit in the P and T diagram. And we can see by solving the determinant L, so we can plot the Z curve explosion limit. And using the linear theory, the explosion limit agrees well at the first and the second limits with the detail and reduce the mechanism. But it deviates a lot at the third limit. So this is what we have seen here. And also based on this linear theory, we try to identify the wall destruction effects on the explosion limit. We try to double the wall destruction reactions rate coefficient for H, HO2, H2O2, and NH2. Now we perturb this rate coefficient. And we see that when we change the rate coefficient, for example, if we change H and NH2 related reactions, we will see that the first explosion limit change. So it given pressure, the temperature increase about 20 Kelvin. And if we change the rate constant of reactions related to HO2 and H2O2, we will see the third explosion limit change a little bit, maybe increase by 20 degree K given a pressure. So that means these reactions are influence different explosion limit. But for the second limit, it doesn't change at all when we perturb the rate constant of different wall destruction reactions. Okay, and finally we come to modify the mechanism, because just now we see at the third limit there is a large deviation. This is because reaction at high pressure conditions, reactions between intermediate species become quite important, increasingly important. So that's why we have some important radical reactions into the mechanism. We call them nonlinear mechanism. For example, the R19 to R22. And after we got these four nonlinear reactions into the mechanism, we would see the linear plus nonlinear mechanism can predict the explosion limit quite well at all the first, the second, and the third explosion limit. Okay, so we come to the summary of part one. For ammonia, the explosion limit curve is monotonic. But if we get hydrogen into ammonia, we got mixtures, the explosion limit changes to non-monotonic curve. And with hydrogen percentage increasing, the H2O2 system reactions become dominant at medium and high pressures, and the reactions involving H2O2 and HO2 play a significant role at high temperatures. Wall destruction of HO2 and H2O2 obviously influence the third limit, while that of H and NH2 affects the first limit. And finally, we built a compact mechanism which is able to calculate the explosion limits of ammonia and hydrogen mixtures. Okay, and the second part of this talk is energy conversion in premix flames of hydrogen ammonia mixtures. So for combustion efficiency, when we talk combustion efficiency is something related to energy conversion. So usually we use the first law of thermodynamics to calculate combustion efficiency. The total fuel energy will be divided into work, heat loss, exhaust energy, if we use the first law thermodynamics. And when we talk about the second law thermodynamics, we talk about the quality of energy. So there are different terms. For example, the availability or exergy or available energy, so forth and so on. So if we use the second law to describe the total fuel energy exergy conversion, it would have 4 parts: work production, exergy transfer due to heat loss, and exergy loss, and exhaust exergy. These 4 parts. And in this part, we try to identify the exergy conversion or exergy destruction in premixed flames of ammonia and hydrogen mixtures. And what we did here is we first solved the combustion system based on conservation equations, and we solved the thermodynamic and the species parameters at each condition. Then we use this result to generate hydrogen, the entropy transport equation. For this entropy transport equation, there are different parts, including chemical reaction, heat conduction, mass diffusion, and viscous dissipation, and incomplete combustion. So, for example, for the chemical reaction, we can use the typical formula to calculate. For example, this one is the summation of mu, which is the chemical potential times the reaction rate divided by T. So this is the entropy generation by chemical reaction. And for the other terms, we can also calculate them. So we do this work at initial temperature of 298 K and the equivalence ratio of 1.0, initial pressure at 1 and 5 atm, and blending ratios of hydrogen change from 0% to 100%. We use the mechanism of an ammonia and hydrogen mixtures, and it's developed by Jiaotong et al., which has 36 species and over 200 reactions. So first we come to the overview of the exergy loss rate curves. So from these 4 figures, we compare the different fuels with different hydrogen blending ratios. But from all the figures, we can see the highest contribution of the entropy generation is from the chemical reaction, which is the purple line, followed by the green line, the heat conduction, and also the red line is mass diffusion. So for all the fuels, they are the same order. But we note that for the viscous dissipation, which is the blue line, it's not shown because it's too small, it's negligible. So in this way, in the next part discussion or analysis, we didn't consider the viscous dissipation related entropy generation. Okay, that is only for the entropy generation rate. And now we come to see the total exergy loss distribution from different sources. And from these 2 figures, the left one is 1 atm, the right one is 5 atm. We can see different parts represent the exergy loss from different sources. So first, we see the total exergy loss. We can see if we get a hydrogen percentage increase, the total exergy loss decrease. And if we get a pressure increase, and the total exergy loss rate decrease. So this is how the hydrogen percentage and pressure change the exergy loss in the premixed flame of the fuel mixtures. Further, we come to see the trend of each source for the entropy generation or exergy destruction. And we can see for chemical reaction, which is the purple part. So with the hydrogen increase, the exergy loss from chemical reactions first decrease and then increase, regardless of the pressures. So this is the number one. And number two, when we talk about mass diffusion and heat conduction here, is the red and black one. So the exergy loss by these two terms decrease with hydrogen increase with. And for incomplete combustion products, the exergy loss just increase with elevated hydrogen percentage. So this is what we observed here. So why we see such phenomena? Then we come to each term, each source, see what happened over there. So first we come to the chemical reactions. We can compare the different fuels. The first one is ammonia. The second one is 30% hydrogen and 70% ammonia blend. And the third one is hydrogen dominant fuel blend. So we can see from the curve, which is the normalized entropy. And the reactions generating nitrogen contributes most to the exergy loss. And if we change the fuel to a hydrogen-dominated fuel, we can see the hydrogen-dominated reactions. For example, H plus O2 and HO2 plus OH. These reactions contribute a lot to the entropy generation. So that's why we see just now the entropy generation would first decrease and then increase with the hydrogen percentage increase, because there are two fuel chemistry competes here. And now we come to the heat conduction. So from these two figures, we observe the normalized entropy generation rate due to the heat conduction. So the x-axis is distance. And we see the decrease of the flame thickness is quite obvious. And this would reduce the entropy generation. And this effect is more than the increased exergy loss rate, the peak one, the peak value here. So the total exergy loss due to the curve change with the hydrogen percentage increase. And for mass diffusion, we will see the most contributing species are reactants.
No, this was
yeah.
Hello, Dong. Yeah, your
yes.
screen got frozen, and on top of that, actually, we need to wrap up. So if you could just either you restart the slide, we cannot see the slides moving forward.
Okay.
Something got frozen. If you could
maybe
just
maybe the network is not stable. I just got a remind from the computer. Does it work now?
No, we don't see that. You probably should restart your screen sharing.
Okay.
Hmm? Yeah, your camera is also frozen, so somehow your connection is you're not moving on your camera either.
How about now?
Let's see, we are waiting.
So still doesn't work?
Yeah, it's not showing up. But I think in the interest of time, you may want to verbally wrap up the talk. I hope you are close to the end.
Okay, now we come to the...
oh yeah, well, we see the summary part now. Okay, please.
Okay, so we just missed the incomplete combustion. But let me use one word to summarize. With the hydrogen percentage increase, we could see that some active radicals and hydrogen percentage in the incomplete combustion products increase. There are more fractions increase. So that's why when hydrogen percentage increase, the Exergy destruction percentage also increase. Okay, now we finally come to the summary. So the total Exergy loss of ammonia premix flame decreased monotonically as hydrogen percentage increase in few blends. And the overall Exergy loss decreased by 1 or 2% as the pressure increased from 1 atm to 5 atm. So then we analyze the Exergy. Increased hydrogen percentage and Exergy
So we
loss.
lost you again.
Yeah.
Okay.
Okay. And thank you for your attention. I'm sorry for the
No problem.
unstable.
Maybe just one quick question.
Well,
Sure.
Go ahead, Don.
Yeah. Hi, this is Hong. Yeah, nice talk. It's very interesting fundamental work. Just a quick, when you talked about this the Z curve and correction with the nonlinear reaction steps you introduced, I was rather surprised because I thought you mean the discrepancy in the third limit was mainly attributed to the presence of the ammonia, but those 4 additional steps you introduced had nothing to do with ammonia. So my question is, are they somehow indirectly related to the presence of the ammonia in the mixture? Or are you meaning that this is
So
improving accuracy for general hydrogen explosion? Well, there's NH2. Yeah, I see that. Okay.
Yeah, so 22 is one reaction related to ammonia. And for the other 3 ones, so they are very important reactions in hydrogen oxygen system reactions. So it covers all the fuels, the both fuels.
All right, thank you.
Okay, well, let's thank
Thank you.
Dong again.